So I want to talk today about products in cohomology. And this will lead us naturally next time to studying the Stony squares, the Stony operations. There are two ways to do this. One is complete abstract nonsense without any formulas, and the other is to write down explicit formulas. And today I will do a mixture of both. Next time I'll actually produce explicit formulas for you, though I will tell you how the general nonsense arguments go. So we start with the Whitney product formula. So this takes two cochains, space, a singular cochains, and produces a new one. The Whitney formula for cup product. So let me tell you what alpha cup beta is by describing how it evaluates on any singular simplex sigma of the appropriate dimension. So if you take the cup product, this is a graded operation, graded preserving operation. You take a P cochain and a Q cochain, and you form their cup product, which I'm going to describe in just a minute. You get a P plus Q cochain. So to describe that cochain, I'll tell you how it evaluates on a singular simplex. That'd be appropriate. I agree. And the formula, Whitney's formula, is to take the product of alpha on the front P face of sigma times beta on the back Q face of sigma. So here, the front P face of sigma is simply sigma restricted to the span of the first P plus 1 vertices. I think if the vertices of sigma is the integers from 0 to P plus Q, I can restrict to the subsimplex span by the first P plus 1 of them, and that's the front P face. And similarly, the back Q face is the restriction of sigma to the last P plus Q, the last Q vertices. So I'm going to work in parallel here with formulas and pictures. So my picture of the Whitney product is this. It's really the sum over all pictures like this. So this is sum K. I'm imagining these are the vertices of the simplex of dimension n, let's say. And so these are the vertices 0, 1 up to k, and these are the vertices k up to n. So okay. So I'm thinking of this picture as giving me an element in the singular chains of the space X tensor the singular chains of X. It's a product of these two chain complexes. And this picture would represent the front K face of sigma into the back n minus k phase sigma. So I guess if I wanted to line up with these formulas, this would be P, and this would be P plus Q. So, P. And of course, here I'm going to sum over P. So I'm going to take all diagrams of this shape where the total number of where the vertices run from 0 to P plus Q, but the break can appear anywhere.
You don't sum in that?
No, I didn't sum here. I could have, and this would only produce one non-zero term. But here I'm going to sum, and then when I go to evaluate cocycles, if I had homogeneous cocycles, only one of the terms would matter, the one who's gave me the right dimensions. So what this picture means is if we have an alpha tensor beta in the tensor product of the singular cochains, so we have a tensor product of the cochain with the cochain, I will evaluate the first element in this tensor product on the upper row and the second element in the tensor product on the bottom row. So this would here be alpha evaluated on the sigma restricted to 0 up to P times beta sigma restricted to P up to P plus Q. Okay. So exactly the formula I wrote down here. Okay, so this is my picture of this Whitney product formula. And if I let alpha and beta vary over all cocycles whose degrees add up to P plus Q, I should evaluate the formula. The way I get this formula for all possible alpha and beta is to apply this tensor product to the sum of all these diagrams. And pick out the one of the right shape, the right size, and all the others would contribute 0. So if I don't specify...
You said cocycles, you mean cochains?
Yeah, these, so far these are all cochains. So that's the Whitney product, definition of the Whitney product, and here's my picture for it. And here's my understanding of how these pictures produce formulas like this. Okay? So the first lemma is that the Whitney product formula, Whitney product defines associative, graded algebra ring with two-sided unit being the cochain evaluating one on each 0 simplex on each point. So of course I mean the Whitney product produces this algebraic structure on the cochains. Makes the cochains into a ring, that is to say an associative ring whose multiplication is associative. Clearly bilinear in the variables A, alpha, and beta, and it has the unit, two-sided unit, this particular 0 cochain. And the proof of that is all completely obvious. check alpha P cup beta Q cup gamma R on sigma P plus Q plus R. I'll write out the formula, and it will be obvious from this formula that if I associate it any other way, I get the same answer. Okay? So first of all, we have to break over this cup product. So it's alpha P cup beta Q evaluated on the front P plus Q face of sigma times gamma on the back R face of sigma. Now I do the cup, I use the Whitney formula again here, and this is alpha P on the front P face of the front P plus Q face of sigma times beta Q on the back Q face of the front P plus Q face of sigma times, gamma on the back R face. Well, now let's just think about what this is. If I take the front P plus Q face of sigma and then take the front P face of that, this is nothing but the front P face of sigma. So here I have the front P face of sigma. Here I have the back R face of sigma. And here in the middle, I have the thing that sits in between them. So we go up to P, and then we go, and this is R. So this is in fact P plus Q, P plus Q plus R. This is 0 P, and so here I have P to P plus Q. So if you will, this is the evaluation of alpha on the front P face, beta on this middle face, which goes from P to P plus Q, and then gamma on the last R face. And that, I'll get the same answer if I associate it any other way. And I think I'll leave the proof of the two-sided unit to unit. Okay? The next thing to see is if this formula behaves well with respect to products, with respect to the differential. So that's a slightly more non-trivial lemma. It says the differential, the co-boundary of alpha cut beta, this is a P and this is a Q, is d alpha cut beta plus minus 1 to the P alpha cut beta. The sort of formula you're used to from the Cohomology sine rule. And I want to prove this both in the picture language and in the formula language. Was there a question?
I just didn't know the wording of the coastal thing, but it's like Latinus. It's another way to.
Yeah. Anytime, this is a operator of degree 1. Anytime you switch two things in graded algebras, you're supposed to put minus 1 to the product of the signs of the two things you've switched. So as I move the d past the alpha, I've got a 1 times p is my minus 1 to the 1 times p. Okay, well this isn't completely straightforward. Let's think about these diagrams. And let's take the boundary. Let's just think of one diagram. So fixed degrees. So P to P plus Q. Here's my diagram. Here's the front P face. Here's the back Q face. And now I have to take the boundary. Which way do I want to do it? Yeah, so let me write down the formula first. So I'll do this, of course, by evaluating on the simplex and then passing the differential over to the boundary of the simplex. So d of alpha p cut beta q on a simplex at dimension p plus q plus 1 is, of course, alpha p cup beta q on the boundary of the simplex, which is summation k equals 0 to p plus q plus 1 of -1 to k alpha p cup beta q evaluated on sigma restricted to 0, skip k. Well, let me try it this way. K face of sigma. So lambda k of sigma is the inclusion of delta k minus 1 into, sorry, inclusion of delta p plus q into delta p plus q plus 1 as the k face. So the vertices, these vertices map in a monotone way, strictly monotone way, skipping k. So then we have summation k equals 0 p plus q plus 1 -1 to the k. Alpha p on the front p face of lambda k sigma times beta q on the back q face of lambda k of sigma. So in this expression, you see, let's just study the structure of this expression. So first of all, the index k never appears in this expression because we've taken lambda k, and that involves all the vertices. That involves the face opposite to the k vertex. So the vertices that will appear in this expression are all those except k. So k is an omitted vertex in this expression. It does not appear. So what happens is you get a picture like one of two types of pictures. You get a picture like this where the k vertex appears here, and p plus q. So that would be when k is less than p. So the emitted vertex is here. The front k face then has that, skips over the emitted vertex. So, so even though this is index p, it's really the vertex p minus 1. Let me see, p minus first vertex, and this is the p minus first vertex, and this is the p plus q vertex. So that's one kind of picture you can have. The other kind of picture you could have is when the deletion occurs after the doubled vertex. So this would actually be p plus 1, p plus 1, p. So those are the two possible pictures that come into this formula. If I'm evaluating p alpha p, a p cochain, kappa q cochain on the boundary.
Can't P be eliminated?
Can?
P itself be eliminated?
No, let's fix the dimensions of alpha and beta.
No, I mean, in this
when
picture
K is
here.
here.
No.
The first picture.
No,
Okay.
that's the point. You cannot eliminate this vertex. Because the structure of this thing is, first you've eliminated a vertex, and now you have P plus Q plus 1 vertices instead of P plus Q plus 2. So one of them somewhere has been omitted. And now you do this process, you go a certain ways, you go down P, then you double, and you continue. So if going to P may already skip over the first omitted vertex, in which case you double afterwards, or it may happen before you get to the omitted vertex, in which case you double before. You cannot omit. So if you omitted if you omitted P here, both places you'd have no repeated vertex and you'd have the wrong dimension. If you omitted one copy of P, you'd have no repeated vertex and no omitted vertex. So you can't do that. In fact, this is the whole point.
So in the summation, we can write K equals to P.
No, the point is, suppose K was P.
Ah.
Okay. Then we want to take the front P face of the P face of sigma. So what is the front P face of the P face of sigma? So the P face of sigma drops out the Pth vertex. So its vertices are 0 up to P minus 1, P plus 1, up to P plus Q plus 1. And now I need to take the P face of this. Well, that's all of these vertices. So this would be the last example of this type. On the other hand, if I delete a vertex, okay, so that's the flat. So these, I mean, as I pictured them, these always go from 0 to P plus 1 with an omitted vertex here, and then P plus 1 to P plus Q plus 1. And these go from 0 to P with an omitted vertex here, which could be P plus 1. Now the other thing I want to do is omit all possible vertices in this diagram. So this is what the formula leads to. It leads to this structure of, so this formula leads to the structure of one omitted vertex, one doubled vertex, the front face is all vertices less than or equal to doubled one, and the back face, I shouldn't say front and back face, I should say the first factor is evaluation on the simplex span by all the vertices less than or equal to the doubled one. And the second factor corresponds to all vertices greater than or equal to the doubled one. Sorry, let me try this again. First factor, the vertices of what you evaluate the first factor on. These are all unomitted vertices less than or equal to the doubled vertex. And the second factor is all unomitted vertices greater than or equal to the doubled vertex. Unomitted. And this is the sum of all of them, all possibilities. And the sign is -1 to the k, where k is the omitted vertex. Right, the sign is -1 to the k, where k is the vertex that's never going to appear. So that's d alpha cup beta evaluated on sigma. Now I want to compare that with what I claim it's equal to. I want to compare that with d of alpha p cup beta plus -1 to the p alpha cup d of beta on sigma p plus q plus 1. So I want to compare. And what happens here is we get all of the terms like this, plus we get more terms where we delete this or delete that. We get 2 more terms. So let's see how that goes. Well, just write out what it is. This is d alpha p on the front p plus first face, the sigma, times beta q on the back q face of sigma, plus -1 to p, and now we have alpha on the front p face of sigma times d beta on the back q plus 1 face of sigma. Okay. So let me write that over here. Now let's push the d across. So this is summation -1 to the k equals 0 p of alpha p on boundary k of the front p face of sigma times beta on the back q face of sigma. I'm sorry, I should have. Yeah, that's right. Plus -1 to the p summation L equals 0 to q. This should have been p plus 1. Q plus 1 of alpha p on the front p face of sigma times -1 to the L beta on boundary L of the back Q face of sigma. Okay. This sign is from the sign here, and this sign is from taking the Lth boundary of the back Q plus 1 face. So what we're doing now is we have a diagram that goes, well, there are 2 possibilities, p plus 1, p plus 1, q, and I evaluate alpha on the boundary of this, which means I drop out every one of these vertices, one at a time, and put a sign in. And then, so that's what the first terms, where they come from. The second terms come from the picture 0 to p. Well, here you put alpha, and here you take beta, where you evaluate the beta on the boundary of this thing. So you will delete one at a time all of these vertices. So now you have three types of vertices, three types of pictures. As long as you don't delete either this vertex or this vertex, you have a picture that appears over here. You have a diagram that appears over here. Namely, you have a deleted vertex somewhere and a double vertex, and the top is all the unomitted vertices up to the double, and the back is all the vertices after the double one, except for the omitted one. So this would be when you're taking boundary alpha, and this would be when you're taking boundary of beta. But we have two extra pictures. We have the one where we drop out of alpha p plus 1. So that would be -1 to the p plus 1, alpha restricted to the front p face of sigma, times beta restricted to the back q face of sigma. And remember, sigma is a p plus q plus 1 dimensional simplex. So that would be this picture where we evaluate alpha from 0 to p and beta from p plus 1 to q. And so that evaluation does not have the structure that we see down here, because it has no deleted vertices and no repeated vertex. Likewise, the other term that contributes is when you drop out the pth vertex, the 0th vertex from the back q plus 1 face. So that would be -1 to the p, alpha on the front p face of sigma, times beta on boundary naught of the back q plus 1 face of sigma. And this is just the back q face of sigma. And you see these two terms have the opposite sign. They have the same exact structure. Alpha is evaluated 0 to p, and beta is evaluated p plus 1 to q, p plus q plus 1. So there are two ways you can evaluate alpha on the first p and beta from p plus 1 to p plus q plus 1. One is to have a diagram like this and take the final boundary p plus 1 for the alpha, or have a diagram like this and take the first face for the back p plus q plus 1 face. So those terms cancel, and all the other terms have exactly the structure here, and all the other terms you see here occur here, and if you check the sign, it's -1 to the index of the emitted vertex. So, just to repeat, there are here two extra terms. Ignoring those terms, the terms you find here are exactly the same, including the sign, as the terms you find here. And the two extra terms both are evaluating alpha on the front p face and beta on the back q face, but they appear on the opposite side, so they cancel. So that's the proof of this limit. And it's not quite trivial. There's this telescoping cancellation here.
Is there an explanation of why they cancel? Like, I know it's fundamental, but
I can't give you a better answer than what's here. And it's embedded in the Koszul sign and the fact that you've doubled the vertex here. All right. So as a corollary, we see that the Whitney cup product, Whitney co-chain cup product, induces a ring structure on cohomology. So the ring structure on the cochains passes to a ring structure on the cohomology. The point is just if you take the coboundary of gamma cup beta with beta cocycle, this is equal to the coboundary of gamma cup beta, because the other term involves coboundary beta, which by assumption is 0. So if you take the cup product of a cocycle with a coboundary, you get a coboundary. Likewise, if you put the coboundary here, similar to the argument. So now, and if alpha and beta are cocycles, alpha cup beta is a cocycle. That follows it directly from this one. So you define, given two cohomology classes, you define their cup product to be the cup product of their cocycle representatives, and then the cohomology class that represents. You have to show this is well defined. Well, first of all, alpha cup beta is a cocycle, so it does define a cohomology class. And if I add here boundary gamma, and add here boundary mu, I get cup product is bilinear, so I get alpha cup beta plus alpha cup boundary mu plus boundary gamma cup beta plus boundary gamma cup boundary mu. And these are all of the form cocycle cup coboundary, cocycle cup coboundary, coboundary cup coboundary. So these are all 0 cohomology. And therefore the cup product is well defined in cohomology. Since I started with an associative ring, if I restrict it to cocycles, it's an associative ring, so it induces an associative ring in cohomology. And we still have a unit. The unit is the cocycle. Evaluating 1. From the cohomology class of the cocycle. Evaluating 1 on every simply that. So that is a cocycle. Coboundary has 2 different points of opposite sign. So it's cochain will evaluate 0 on boundaries of 1 cycles. But you get an associative cohomology ring with a unit. Now, you would expect this ring to be graded commutative. Think about differential forms, right? Differential forms are somehow linked to singular cohomology. But it's pretty clear that this cochain formula doesn't have any symmetry. There's no relationship, obvious relationship, between alpha cup beta and beta cup alpha. So alpha cup beta and beta cup alpha are not related in any obvious way. It's certainly not true that alpha cup beta on the cochain level is up to a sign beta cup alpha. but it is nevertheless true the ring structure on cohomology is graded to be. And this is a cohomology class of alpha times the cohomology class of beta is -1 to the degree of alpha and the degree of beta cohomology class of beta times cohomology class of alpha. And the proof of this is what I want to talk about next. And there are two ways to do the proof. I'm going to not write down explicit formulas. I'm going to use this general notion of basically carriers. I'll talk a little bit. So I'm mixing here. I wrote down an explicit formula for the Whitney cochain cup product. And now I'm going to prove it's graded commutative by a general argument. I could have used that same general argument to prove there was a cochain formula, and then the second part, which I'm going to do now, would show that the induced cup product in cohomology was independent of that formula. All you need is a natural formula that's local and agrees with the obvious cup product on zero cocycles or zero cochains. That's all. And this happens to be a beautiful formula. It's well known, but there's lots of other formulas you could write down to give the same answer in cohomology, though it might give very different looking answers at the cochain level. Next time, I will give you explicit formulas to show this graded commutativity of the Whitney product structure. These formulas go back to Steenrod, and they were discovered before the general nonsense argument of any local formula has to work.
Is there an analog algebra structure on CW cochain?
Not so clear. I mean, there is this general yoga, shall we call it, that will work in the CW context.
A general what, sorry?
Yoga principle, heuristic, that if you can write down a formula that's natural and local and is what it's supposed to be on zero cochains, then it will give the cup product. But there's no natural formula like this that I'm aware of for CW complexes, or even regular cell complexes. All right, so, sorry, what do you mean by local formula? So in the case of a simplicial complex, let's say it this way. So when I have a simplicial complex, I look at the n-simplex. Let that be the n-simplex. And have a singular complex. Into the singular complex. I want something associated, say, Whitney of delta n, some formula in here. And so it's got a first component, or it's a linear combination of a first component and a tensor a second component. But it has to be local in that if I start with the simplex, I get something in the simplex cross the simplex. So suppose I have an element like that. Let's call it Whitney sub n, or Whitney of delta n. And it's going to have some properties. I'm going to talk about those in just a minute. But compatibility with boundary. Then in the singular complex of X, I would define the Whitney product. By saying what it does to a singular simplex, sigma. So what is Whitney of sigma? Now sigma is an n simplex. Well, it's simply sigma tensor sigma, a sigma star tensor, sorry, sigma star of Whitney delta n tensor. I guess you should call this sigma cross sigma. Not sure what to call it. In other words, you associate it to delta n, you have an element in the tensor product. So some singular simplex here, tensor singular simplex here, a linear combination of them. Well, now you use sigma to map the delta n into x, and you use sigma to map delta n into x, and you push forward these tensor products. So maybe you want to call this sigma star tensor sigma star. That's the right thing.
Is this a cyclic thing?
Is it what?
What is this? Why are you talking?
Say, make a whole question?
Why do we consider this?
Why do I consider this?
Yes.
Somebody, maybe it was you, asked me what local meant.
Oh.
So that's the definition of a
Yeah,
local formula.
yeah, it's natural and it's local. So that when you apply it to one particular simplex, you don't ever go outside the simplex cross the simplex. In some sense. In this algebraic sense of, well, we're allowed to use singular things in the first factor, tensor singular things in the second factor. So our formula is not allowed to go out somewhere else. It has to be concentrated in a diagonal in x cross x. Of course, I'm working algebraically rather than geometrically.
So is there a formula for, like, for cubical cohomology?
Well, you could
Someone
write
asked
down-
about CW complexes in general, but more.
Yeah, if you have a regular cell complex, then you can do the same sort of thing. But what I don't, if they're cubes, I could write down a formula for you. More generally, these sort of arguments will show there are formulas, but is there a nice one? I mean, suppose you use pentagons as we know what forms. But the same thing would make sense. Suppose this is any cell, and I could take the cell, cross the cell, and I could look for an element Whitney of the cell in this tensor product and push it forward. And if it has appropriate compatibilities under boundary, that will work. So this whole mechanism goes under the rubric of acyclic carriers. In this case, the carrier associates to each simplex delta n the product of delta n with itself, which is acyclic, or actually associates this chain complex, which is a tensor product of acyclic chain complexes, so it's acyclic. And then you build the formulas using those carriers. The formulas have to lie inside the carrier. So for each simplex, you need a formula that lies inside the carrier of that simplex. And the carrier has to be acyclic. Well, I'm sort of getting a little bit ahead of myself. But. So let me just remind you. So if we take the tensor product of two chain complexes, in the boundary map, A tensor B is boundary A tensor B plus -1 to the degree of A tensor B. We already talked about that formula. So similarly for cochains, dual cochain complexes, again, we have alpha tensor beta, alpha tensor beta, plus minus 1 alpha, alpha tensor d beta. So those are conventions on how boundary and dual differential act. These are dual operators if you make the following non-causal identification of this with the dual of that. So alpha tensor beta on A tensor B, the duality is this is alpha A beta B, which is a rather strange duality formula. But it's the one that's consistent with these rules. The reason it's strange is it doesn't satisfy the causal sign. I'm moving a beta past an A, but I don't get minus 1 to the beta times A. Now, somebody who's versed in algebra can tell me why we screwed up here. Why this sign? I mean, mathematically it's fine, but it's a weird sign. So a weird sign comes from the fact that we weren't careful. If we write a formula like this, E alpha on A is alpha on boundary A, that's where we made the mistake. Because in some sense we pushed the D past the alpha and we didn't put in the sign. So the right way to do this so that you get the causal signs here, but I'm not going to do it because nobody ever does, and this is set for 70 years in mathematics, is of course, if we do it this way, if we put the cocycles here and the cochains here and the chains there, this should be alpha acted on by E A. So our differential should act from the right, not the left. And then our sign rule would change. This sign rule would change. The sign would occur here because the D is coming from the other side. So I'd write this as beta D tensor alpha plus, and here would be the sign, minus 1 to the beta. And then you get the causal sign. So, for those of you who like algebra. But we're not doing that. But I'm just pointing out this leads to a weird formula for the duality. But this is the duality consistent with this and this kind of formula. You don't get a choice. Okay. So that's the context in which we're working. All right?
No one's going to change it?
Huh?
No one's going to
No. You know, it's like cohomology. Homology should be called cohomology, and cohomology should be called contra-homology. Because homology is covariant functor and cohomology is contravariant functor. But nobody is ever going to make that change, even though it's mathematically speaking, logically speaking, the right way to name these things.
Didn't Hilton and Wiley try that?
Somebody tried way back when, and it failed. It's like the Avenue of the Americas, right? I mean, some things are just so embedded that it's impossible to change them. And this is one. Okay. So we have defined, now defining Whitney delta n inside singular chains of delta n and into the singular chains of delta n. Actually, it's in the simplicial chains, but it's okay. And it is summation over k, front k face of sigma tensor back n minus, maybe I call it something p, n minus p face of sigma.
Sorry, what does Whitney, what is the argument to Whitney?
Ah, you're right, there's no sigma here. So I should just write. So this means the inclusion of the front p face of delta n in the delta n. So that's the singular p simplex of delta n. This is the inclusion of the back n minus p face of delta n into delta n. That's a singular p minus n simplex here, and I take their tensor product, and that's sum over all p. You want to ask again? Let's give him a chance.
I'm fine with this. I'm just using notation. It's
Okay. You had a question?
I always find this definition unnatural, because why do we choose the front P, but not choose all of P things and then maybe time it with a sign and then
You could.
we'll get the same theory?
Yep.
Does that help the graded commutativity?
No.
No?
It's the same issue. In fact, if anything, it's going to make it worse. And your formula has to work for the zero simplex. For the zero simplex, it has to be the identity tensor of the identity. And it has to be compatible with boundaries. That's it. And it has to be local like this. That's it. Any formula like that. Compatible with boundaries, works on the zero simplex, compatible with boundaries, and carried like this is a good formula. Gives the same answer. Cohomology. Okay. All right. So that's my Whitney chain, and now I can define Whitney from singular of x into singular of x, tensor singular of x, by telling you what it does on a simplex sigma in the n simplex, a singular n simplex. Well, this is what I just said before. It's sigma star tensor sigma star of Whitney of delta.
What is sigma star?
This is an element in the tensor product of the singular chains on the simplex, tensor itself. Sigma is a map from the n simplex to x, so you get an induced map on the singular chains, just composed with sigma. So that's what I'm doing. Compose the front face with sigma, compose the back face with sigma. That's just taking the front face of sigma and the back face of sigma. This is the formula I wrote down before. Okay.
Wait, so an example of a formula that's not local is just something that doesn't extend linearly from the
No, these formulas have to be linear.
Sorry, so then what exactly does it mean for the formula to be local in this definition?
Well, it means this, so that when you apply it to a singular simplex sigma,
It agrees with.
it comes from, you have something on delta n cross delta n, or you have something in the tensor product of the singular chains. It doesn't have to be a face evaluation. A face evaluation could be some crazy, use nonlinear, if that's what you mean, nonlinear singular chains here. That's okay. It could allow you to curve them if you want, as long as it's compatible with boundary and it comes from some formula here. Okay. And what we just proved a minute ago is that Whitney is a chain map. where here you use the boundary map in the singular chains, and here you use this boundary map in the tensor product. So if you look back at what I was proving this.
Do you call this a coproduct?
Sorry?
Do you call this a coproduct?
Yeah, this is a coproduct. So that's the already given proof. Think about it. Let's see. Now on sigma tensor, on singular star x tensor singular star x, there's an involution t switching the factors. It sends A in degree P, tensor B in degree Q to minus 1 to the PQ, B tensor A. It's a flip of the two factors here. But in order for this to be a chain map, you have to put in a sign, and the correct sign is PQ, minus 1 to the PQ. And so it is compatible with this formula, the Cohomology sign. So we have now two chain maps. So this is a chain map. The P composed boundary composed P. That's why you need this sign. Okay. So now I have two maps. Whitney and singular of x into the tensor product. That's one of them. And the other one is T composed with Whitney. Do Whitney and then flip. So these are two chain maps. The lemma tells me this is a chain map, and the fact that T is also a chain map then follows that the other one is a chain map. So two chain maps, and the theorem is T composed Whitney and Whitney are chain homotopic. This is the analog in the category of chain complexes of homotopy for topological spaces. Yeah.
Could you please get the definition of T again?
Of T,
Yes.
flip the factors and put in a minus 1 to the PQ. P of A, P, into PQ, minus 1 PQ, PQ. Flip the factors with the sign. Well, let me just remind you what a chain is. Chain homotopic between two chain maps. So, that is to say, there exists a linear map H from the domain chain complex to the range chain complex. And now, God only knows, I can't keep this straight. Raises degree by 1. So let me. So there exists a H is linear, and H raises degree by 1. It sends a K chain to something where these two add up to K plus 1. And it's not a chain map. It satisfies the relationship BH plus H, boundary H plus H boundary is P composed with Whitney minus Whitney. So when I say two chain maps between complexes are chain homotopic, I mean there exists an H so that you can plug in this, so that this formula holds for that H. Well, a corollary of that, just as in topology, if you have homotopic maps, they induce the same thing in homology. This implies that P composed with Whitney and Whitney induce the chain map in homology. But even better than that, and more relevant to what we're interested in, is that if alpha and beta are cocycles in sigma X, then alpha tensor beta on Whitney of sigma equals alpha tensor beta on T composed Whitney of sigma. Let me argue that, and then let me deduce from that the sign commutativity of cut product. So let me prove the corollary. Let's take the difference. Let's take alpha tensor beta evaluated on T composed with Whitney of sigma minus Whitney of sigma. Well, I have a formula for that. That's alpha tensor beta evaluated on boundary H of sigma plus H boundary of sigma. Well, now using the relationship between boundary and D, which is D of alpha tensor beta on H of sigma. That's this term plus H star of alpha tensor beta evaluated on boundary sigma. That comes from this one. So just using the adjointness. So this H is the induced map on chains, and this is the pullback, the dual map on cochains. And I'll do one more step, push the D, the boundary to a D. Well, this is 0, since alpha and beta are cocycles, and hence their tensor product is a cocycle. Okay. So I have the formula for that. The evaluation of this cocycle on Whitney minus the evaluation on the flipped cocycle on Whitney is equal to, this goes away, BH star alpha tensor beta on sigma. Well, that's supposed to do it. Yeah, so let me write this one this way. The difference of these two chain maps evaluated on sigma. Okay. Now I want to evaluate this side. So alpha tensor beta on Whitney of sigma is alpha cut beta on sigma. That's what this gives me. And this, because of the sign, is -1 to the dimension of alpha, dimension of beta, beta cut alpha on sigma. Because the sign flips the two, so if I have front face, tensor back face here, when I flip them, I get back face, front face with the sign. So I'm evaluating alpha on the back face and beta on the front face. Well, that's what this is. And this is the sign. So I see that evaluating this and evaluating this on sigma give the same answer. That's true for every sigma. That means those cocycles are the same. Thus, -1 to the PQ beta of alpha minus alpha of beta is D of H star of alpha tensor beta. So the difference of these two cocycles is a coboundary. So that implies -1 to the PQ beta of alpha minus alpha of beta is exact. D of this. And that means, well, it is 0. It's the exact cohomology class, which is 0. So -1 to the PQ beta alpha is alpha beta. So that is how we're going to prove the sign commutivity of Whitney cup product. We're going to compare the Whitney map with the Whitney map composed with flip and a sign. And we're going to show those maps. If those maps were the same, then I'd be done. Then on the cocycle level, the thing would be sign commutative. They're not equal, but they're chain homotopy, which is good enough.
Do you,
What you have just shown there, is it the same as this carbon?
Yeah, I sort of switched in midstream, didn't I? If alpha, beta are cocycles, then this is equal to that. And no, that's not right. If alpha, beta are cocycles, then alpha tensor beta, what I proved is alpha tensor beta -1 to the PQ, alpha tensor beta, well, what I've shown was alpha tensor beta on T composed with Whitney is equal to alpha tensor beta on Whitney of sigma plus D of something evaluated on sigma. That's what I should say. So the difference of these evaluations is D of something that depends on alpha and beta evaluated on sigma. And that something, here's the formula for it. It clearly involves alpha and beta, but it also involves this chain homotopy H. So that's what I proved. And then that's step 1. And step 2 is alpha of beta. Is -1 beta. I'll prove both of those.
In this whole discussion, do we know anything about this Whitney except that it's local and?
That's all I'm going to use. Now I'm going to prove this, and all I'm going to use about the Whitney is it's in here and it's a chain map. I mean, it's in, for each simplex, it comes from the simplex, across the simplex, and it is a chain map. So, in fact, let me specify that. So even though we have an explicit formula for Whitney, I'm not going to produce an explicit formula for H, though I will next week. And the only thing I need about Whitney, so we use only that Whitney is a chain map, and Whitney is sigma star tensor sigma star of some universal element Whitney of delta n. That's the only two properties.
That second property is the local thing?
That's the local thing, right? Basically carry. Well, I guess I'm also going to use the fact that Whitney of delta naught is delta naught. It's the identity into the identity in the delta. It's the only thing, I guess. So it starts off correctly. So for example, you can't put 3 times the identity tensor the identity for delta naught. That's obviously not going to give the right answer on cup product of H naught. Cup product of H naught, you have the constants inside H naught, and which are the integers, and the multiplication of restricted to constant has to be the multiplication on the integers. So
Where does acyclic come into this picture?
well, you're going to see, but this chain complex has no cohomology.
Has no.
Sorry?
That chain complex has no
No homology.
no homology.
Except in degree 2. That's what acyclic. Yeah.
Can you write that chain complex in terms of another chain complex of a space, a singular chain complex of a space?
You can write it in terms, well, if I put the simplicial chains here, then you could write that in terms of the cellular chains of the product cell structure on sigma cross sigma. So sigma cross sigma isn't a simplex. Sigma n, delta n cross delta n isn't a simplex, but it's a regular cell. Delta 1 cross delta 1 looks like this. It's not a simplex. But it's a regular cell. It has faces, which are themselves cells, and so on. I could take the cellular homology of this thing. And if I use these simplicial chains here, then I would have some relationship. All right. So those are the 3 things I need. It starts off the obvious way it should start off. It's local. It's a local formula, so you do a formula for each n-dimensional simplex, and you push forward under the singular chains. And the entire Whitney is a chain map. So we construct by induction elements H n in singular star delta n insert singular star delta n of degree n plus 1 such that boundary delta n of plus delta n minus 1 of the boundary of the simplex, I'll talk about what I mean by that in just a second, is equal P composed with Whitney of the simplex minus Whitney composed with So I think this is a formula inside singular delta n tensor singular delta n. So that's where this lies. That's where this lies. Hn plus Hn is an element in singular tensor singular of degree n plus 1. When you take its boundary, you'll get something in singular tensor singular in degree n. So this one lies there. The only thing that needs any explanation is this one. Well, Hn minus 1 is defined on n minus 1 simplices. You think of the boundary as being a linear combination of n minus 1 simplices mapping n with signs. And then you just push forward under those maps the elements h n minus 1. So to expand this out, h n minus 1 boundary delta n is the summation from k equals 0 to n minus 1 to the k, the kth face of sigma star of h n minus 1 of delta n. So this is an element in the tensor product. Well, I guess there's two of these here, right? So for each face of sigma, you have that face included into sigma, so you have the face cross the face included into sigma cross sigma. You push forward this element hn under that face inclusion. That's what this is, and you add them up with the signs. And that's what I mean by this.
Can you write that bigger? Sorry.
Yeah. Sorry. So the boundary is sum from k equals 0 to n minus 1 to the k of lambda k of sigma. This is the kth face. So so this is an element in the tensor product of the singular chain complex of the n minus 1 simplex with itself. These are inclusions. This is an inclusion of the n minus 1 simplex and the n simplex. Here's another copy of it. So just take that map on the tensor product and add them up with the appropriate sign. So that's how this term gets into be an n chain in the singular tensor product. So we're going to, by induction, define maps like that.
Wait, so you're proving what the statement you're just about to erase here? There exists an
No,
H?
yes,
Okay.
yes. I'm proving this theorem, and this was the explanation of what that theorem meant. Okay. Well, we go by induction, and here's where I use my first axiom, H naught in saying of a point, delta naught, tensor saying of delta naught is 0. So because Whitney of delta naught is the identity tensor of the identity, and so T composed with Whitney of delta naught is the identity tensor of the identity minus 1 to the 0, 0. So these are equal. So at this level, things commute. So I take H naught equals 0. And there is no H minus 1, and this formula holds. This side is 0, and this side is 0. Suppose by induction, I have defined the HK, the HL, as required up through n minus 1. Suppose by induction, then greater than or equal to 1. Okay? I need to find an HN. In degree n+1, solving the equation, boundary Hn is equal minus Hn minus 1 of boundary delta n plus P composed with Whitney of delta n minus Whitney of delta n. Right? So I have now given a cochain in degree n here in this complex. I have to write it as the boundary of something in degree n+1. Okay. Well, there are 2 steps to this. Step 1, check the right-hand side is closed. After all, if this thing is going to be exact, it better be closed. And 2, use the cohomology of sin star x versus sin star x is delta n is 0 for all star greater than 0. That's the acyclic carriers. So this thing that we're working in, this complex, is trivial homology. Okay. Well, this is a tensor product of 2 acyclic complexes, and it's an easy exercise. Version of the Kuhn theorem that says the homology of complexes like that is acyclic. All right. So it really remains only to do number 1, show that this thing is a cocycle. If this thing is a cocycle, then we just say acyclic carriers, and we know we can find an HN. And notice this doesn't tell me anything about how to construct it. It doesn't give me a formula at all. It just says you can find it. Given what you've already done, you can make the next step. And of course, it's going to depend on what you've already done, and we have no formula whatsoever. All right. How am I doing on the time?
Almost.
No, 1 minute. Well, let's take the boundary of the right-hand side. Boundary of minus Hn minus 1 of boundary delta n plus P composed Whitney of delta n minus Whitney of delta n. Well, that's 0. Well, this is minus boundary Hn minus 1 of delta n. These guys are chain maps, so I get to push the boundary through. On the other hand, what formula do I have? By induction, I have the formula that's my inductive formula, applied 1 level down. Well, boundary, 0. My term goes away. And you see that boundary of this thing is exactly the difference of T composed with Whitney minus Whitney applied to the boundary. Well, there it is. This is equal to that. This difference is 0. So this thing is a cycle. Therefore, it's a boundary. Therefore, you can construct an H and minus one. There's your chain approximation to the diagram.
Just a minute, chain approximation to the diagonal, you haven't said anything like that before.
I'll talk about that next time. And no, I just said it was a chain homotopy.